Okay, let's dive in. We are getting into something really fundamental today, aren't we? How neural networks actually, well, learn.
We really are. It's the maths engine, the calculus running underneath so much modern AI.
And yeah, that word calculus, it can make people nervous.
Right. But let's be clear. This isn't going to be a abstract math lecture.
Yeah.
We're using our source material here to see how specific bits of calculus, particularly the chain rule, are used in machine learning for backpropagation.
Exactly. Think of it like we're taking you on a guided tour. We want to understand the why. Why do these networks adjust their internal knobs, the weights and biases the way they do? We're aiming for the core ideas.
Yeah, cutting through the maybe denser parts to get the gist.
Huh.
Our mission really is figuring out how the network calculates sensitivity. How sensitive is its error, the cost to each of those internal weights and biases.
Because knowing that sensitivity tells it exactly how to tweak those knobs to get better,
Right.
to reduce the error efficiently.
Precisely. It's how it assigns blame or credit for the final error back through the network.
Okay, so how does it even start doing that? The source material simplifies it a lot initially. Like, picture a tiny network.
Yeah, super simple. Just one neuron in one layer, say layer L1, connected to just one neuron in the final layer, layer L.
Even in that simple case, the question is the same.
Yeah.
How sensitive is the final cost, C, to that last connection's weight, WL, and its bias, BL?
If we nudge that weight, WL, just a tiny bit, how much does C change? That's what we need to know. That's the derivative, essentially.
Okay, so let's lay out the pieces in this mini network. You've got the output, the activation from the neuron before the last one. Let's call that AL1.
Right, and that AL1 gets multiplied by the weight, WL. Then the bias, BL, is added. That gives you a combined value, the weighted sum, CL.
And the DL goes through some kind of activation function, right? Like a sigmoid or ReLU.
Exactly. It gets squashed, you could say, to produce the final output of this last neuron, AL.
And then we compare that AL to the desired output, the target, Y. And the cost for this one example, C0, is just a difference squared, ALY squared.
That's the one. And yeah, quick note, like the source says, those L superscripts, they just mean layer L. They're not powers or anything.
Got it. So the flow is AL1, WL, BL combined makes ZL. ZL becomes AL compared to Y gives C0.
Yeah, that's the path.
And we want to know, how does changing WL way back at the start of that little chain affect C0 at the very end?
And this is exactly where the chain rule comes in. It's essential because WL doesn't directly hit C0.
Right. Its influence has to go through ZL first and then through AL before it impacts the cost C0.
Exactly. The chain rule lets us multiply the sensitivities along that path. It breaks down the overall effect into steps.
Okay, so it's like the effect of WL on C0 is, well, how much does AL affect C0 times how much ZL affects AL times how much WL affects ZL.
You got it. That's the intuition. Mathematically, the source writes it as del C del WL equals del C del L times del C del WL, a product of those three rates of change.
Okay, let's break those down based on what the source says. That first one, del C D AL. How sensitive is the cost to the final output?
For our squared error, C0 equals ALY squared, that derivative is just 2 times ALY.
And that makes sense. The bigger the error, the bigger ALY is, the more a small change in AL is going to impact the squared error. It's the core error signal itself.
It absolutely is. It tells the network how far off it was and in which direction. Super important.
Okay, then the middle part, del A, LDL. Sensitivity of the output activation to the weighted sum input.
That's just the derivative of whatever activation function we're using, sigmoid prime or ReLU prime, whatever it is evaluated at ZLL. It tells you how responsive the neuron's output is to its input right at that point.
Right. And the last piece for the weight sensitivity, del ZL, del delay LL. How much does the weight affect the weighted sum?
Well, remember, ZL is WL times AL1 plus BL. So if you take the derivative with respect to WL, you're just left with AL1.
Ah, okay, that's quite neat. So the impact of changing the weight WL depends directly on the strength of the signal coming in from the previous neuron, AL1.
Exactly. If AL1 is 0, changing the weight does nothing to ZL. If AL1 is large, changing the weight has a large effect. The input gates the weight's influence.
It connects slightly to that neurons that fire together, wire together idea, doesn't it? The connection strength, weight, matters most when the input neuron is actually firing.
It has that flavor, yeah. And one crucial thing the source points out, this whole calculation is just for one training example's cost, C0.
Right. The overall cost function is usually an average over many examples.
So, and to get the derivative for the total cost, you'd calculate this chain rule product for every single example and then average those results. That averaged value is the component of the overall gradient corresponding to the specific weight, WL.
Okay, one piece of the puzzle. What about the bias, BL? How sensitive is the cost C0 to that?
It's very similar. Again, you use the chain rule. The path is BL to ZL to AL to C0.
So the first two parts are the same. Del C, del AL, and del AL, del ZL.
Identical. The only difference is the last step. Del ZL, del BL. How sensitive is the weighted sum to the bias?
And since ZLLA, del 1 plus BL, the derivative with respect to BL is just 1.
Just 1, exactly. The bias adds directly to the weighted sum. Its influence doesn't depend on the input activation, AL1.
Okay, so we can find the sensitivity of the cost to the weights and biases right at the end of the network. But the name is backpropagation. How do we go backwards?
This is where the propagating part really comes in. We use the chain rule again, but this time to find how sensitive the cost C0 is to the activation of the previous layer's neuron, AL1.
Why do we need that sensitivity? How sensitive the cost is to AL1?
Because AL1 is the result of calculations in layer L1. It's the output of that neuron. If we know how much the final cost C0 depends on AL1, then that sensitivity value acts like an error signal for that neuron in layer L1.
I see. It tells the neuron in layer L1 how much its output contributed to the final error.
Precisely. And once we have that error signal for AL1, we can then use the exact same chain rule logic to figure out the sensitivities of the weights and biases that fed into AL1 from the layer before that, layer L2.
So it's recursive. You calculate the error signal for a layer's activations based on the error signals you already figured out for the layer after it.
Exactly. You need del C, del AL1. How do you get that? Well, the influence of AL1 on C goes through ZL and then AL. So using the chain rule again, you'd involve terms like del C, del AL, del ECL, and critically, del ZL, del L1.
And what's that last one? Del ZL, del N. How does the weighted sum depend on the previous activation?
From ZL, WLA, L1 plus BL, that derivative is just WL, the weight connecting them.
Okay. So the sensitivity propagates back, and its magnitude depends on the weight of the connection that's propagating through. Makes sense.
It does. So you calculate the sensitivity for AL1. Now you have the error for layer L1. Then you repeat the whole process. You use this new error to find sensitivities for weights and biases in layer L1 and also the error for the activations in layer L2. And you just keep going back.
Layer by layer, all the way to the beginning of the network. That's the back part.
That's the back part.
Okay, that clicks for the simple one neuron per layer case. But, real networks have loads of neurons in each layer. Does this just become impossibly messy?
That's the natural question. The source material says, well, it adds complexity with more indices to keep track of, but the core equations are, and I quote, essentially the same.
So more bookkeeping, basically. Instead of just one activation AL, we have a whole vector of them. Let's say ALJ is the activation of the JET neuron in layer L.
Right. And a weight isn't just WLL, it's WLJK. That's the weight connecting neuron K in the previous layer, L1, to neuron J in this layer, L. You need two indices now.
Okay, and the cost function changes too, presumably.
Yeah, instead of just ALY squared, if you have multiple output neurons, the total cost C is the sum of the squared errors for all of them. So you sum over J, LJ, Y, JK.
But if we want to find the sensitivity of that total cost C to one specific weight, say WLJK, does the chain rule calculation still look fundamentally the same? Still that three-part multiplication?
The source confirms yes, the form is the same. Del's C del WLJK still breaks down via the path through that specific weight's destination neuron J. So it involves the weighted sum Z LJ and the activation LJ.
Okay, so finding the sensitivity to a specific weight isn't fundamentally different. Where does the main conceptual change come in with multiple neurons?
The key difference arises when you propagate the error sensitivity backwards to find the sensitivity of the cost C with respect to an activation in previous layer. Like finding del C del A L1K, the sensitivity to the output of neuron K in layer L1.
Why is that different now?
Because think about it, that single neuron K in layer L1 doesn't just send its signal to one neuron in the next layer, layer L.
Oh, right. It probably connects to many neurons in layer L. Neuron 0, neuron 1, neuron 2.
Oh.
all via different weights like WL0K, WL1K, WL2K.
Exactly. So the influence of AL1K on the total cost C doesn't just travel along one path. It travels along multiple paths, one through each neuron J in layer L that it connects to.
Ah, okay. So to get the total sensitivity of the cost C with respect to AL1K, you can't just look at one path. You have to add up the influence from all the paths.
Precisely. You calculate the sensitivity contribution that flows back from neuron 0 in layer L using the weight WL0K. Then you calculate the contribution flowing back from neuron 1 in layer L using weight WL1K, and so on. And you sum all those contributions together.
So the error signal arriving back at neuron K in layer L1 is the sum of the error signals propagated back from all the neurons in layer L that it originally sent its signal to, weighted by the connection strengths.
You've nailed it. That summation, that collecting of influences from all the downstream paths, is the crucial difference when you move to multiple neurons per layer. The source indicates that understanding the summation is pretty much it for the main conceptual leap.
And once you have that sum sensitivity for AL1K, that becomes the error signal you use to calculate the derivatives for the weights feeding into neuron K from layer L2 and to calculate the error for layer L2 activations, again using the summation rule.
Exactly. The pattern repeats. Calculate activation sensitivities by summing incoming error signals from the next layer, then use those activation sensitivities to calculate weight and bias sensitivities for the current layer's connections. Back and back it goes.
Wow. Okay. It's intricate, but it's systematic. It's like a very careful, structured way of distributing the blame for the final error back through this complex web of connections.
That's a really good way to put it. And all these derivatives we've been talking about, del W, del C, del B, computed using this chain rule process, they are the components of the gradient vector.
The vector that points in the direction of steepest ascent of the cost function.
Right. And backpropagation is essentially calculating the negative of that gradient, which points in the direction of steepest descent. That tells the network precisely how to adjust all its weights and biases simultaneously to reduce the cost most effectively. That is learning.
So this chain rule machinery, with the summation step for multiple neurons, is the absolute core of how these networks learn from data.
It really is. And yeah, as the source implies, and as we've seen, it has multiple layers of, well, complexity isn't quite right. Maybe intricacy. It can take a bit to fully digest how all the pieces fit together.
Absolutely.
Yeah.
It might be worth revisiting the source material or this discussion again for it to really sink in.
For sure. It's a deep process.
But hopefully, by walking through the chain rule for that simple case, seeing how the sensitivity or error propagates backward, and then crucially adding that summation step needed for multiple neurons. Hopefully, you, listening, have a clearer feel for the mathematical engine driving it all.
Yeah, the core idea remains.
Yeah.
Breaking down this huge, complex, network-wide influence into a series of manageable, local, derivative calculations that get chained together and summed where necessary.
Okay, so to wrap up, let's leave you with a thought to mull over. We've focused a lot on the mechanics of the calculus, the chain rule itself. But how might the actual structure of the network, things like how many layers, how many neurons, maybe even skipping connections, and critically, the specific choice of nonlinear activation function, like sigmoid versus real U versus something else. How do those design choices fundamentally shape these derivatives we just calculated and therefore shape the network's ability to learn certain kinds of patterns effectively? Something to think about.